Thank you, Manuel. Thank you for the invite, and thank you to the students for joining. It's a pleasure to be virtually attending the Cardinal Database Seminar. And as Manuel said, my name is Arun Kumar. I'm an associate professor of computer science and data science here at UC San Diego. Now, it's no secret that we are now in the golden age of machine learning and AI. All the major web companies are using ML extensively for all sorts of products, and that has led to enormous excitement in several enterprise application domains for tools and products that make it easy for them to adopt ML and AI into their data analytics applications. This includes healthcare, insurance, retail, finance, telecom, and so on. And also in the academic domains, virtually all domain sciences and even digital humanists are excited about applying ML and AI for understanding processes in their fields. The International Data Corporation, which is a market research firm that studies data software, has estimated that over the next 2 years, the market size for products in this space of large-scale data analytics, ML, AI, and so on could hit $500 billion. That's an astonishingly large number, but that's what the IDC estimates. Naturally, there's a lot of activity in this space. Several popular open source tools exist for ML and AI. You might have used some of these yourself. And all the major cloud giants are actively working on building ML AI services to get a slice of this pie. In spite of all this progress, as I will explain today, there still remain numerous fundamental efficiency and usability bottlenecks in the end-to-end process of building and deploying machine learning applications. And at the end of the day, that's what my research is about: building new abstractions, algorithms, and software systems to mitigate those bottlenecks and help democratize ML and AI-based data analytics from a data management and systems standpoint. And what do I mean by democratization? To be precise, I mean the following: improve the system efficiency of this whole life cycle, which means make the software faster, reduce resource requirements, reduce costs, and also improve the human efficiency, improve the productivity of the people involved in the loop, people like data scientists, ML engineers, and so on. This requires unifying these areas of data management, ML AI, and also straddling the whole system stack. More concretely, in my work, I study practical and scalable data systems for machine learning and AI analytics that are inspired by the principles of relational database systems that we have been studying for almost half a century now, but also exploit insights from statistical and computational learning theory and optimization theory, which are at the root of what ML computations are about. I have interacted with over almost 4 dozen now data scientists, ML engineers, data analysts, business analysts, domain scientists in all sorts of data science settings: enterprise, web, healthcare, academia, to understand the end-to-end picture of the machine learning application lifecycle. Based on my conversations, I decomposed this lifecycle into 3 major phases: source, build, and deploy. In the source phase, they take their raw data sets that sit in their data repositories, like multi-table relational databases, text corpora, multimedia data, time series data, and so on. And then they convert them to a machine learning ready form, an ML ready data sets that they could use for the next phase, which is the model building phase. In the model building phase, they convert the ML ready data into prediction pipelines that they can use for their application. This is where they do things like feature engineering, algorithm search, hyperparameter tuning, and so on. And then in the deploy phase, they take the prediction pipelines, plug it into their applications for delivering predictions and analytics. This could be just integrating it with the DBMS or other data systems for business intelligence and reporting purposes, for presentation purposes, or it could be integrating it with online services for web pages and IoT devices and so on. They also have to monitor and maintain these models because the application evolves, the data evolves, so they have to oversee this whole life cycle. Across this life cycle, they use data systems and ML system implementations to execute and steer these phases. Now, in this context, my research, I focus on abstracting fundamental steps, key steps across this whole process that are bottlenecks. And I formalize the computations involved in those steps from both the data flow standpoint and from the algorithmic statistical standpoint. And by doing this, it allows us to automate some of the manual grunt work that goes on today and improve their productivity. And because we have formalized the computation, we can now use database and systems-inspired techniques to optimize the execution and improve system efficiency as well. And I've done this for several kind of application contexts, for several sort of fundamental bottleneck steps in this entire life cycle. The link there is my research group webpage, so please go take a look if you're interested in all the projects that we've been up to. But for today's talk, I wanted to focus on a higher level theme that spans my almost a decade of research now in the intersection of ML databases and systems, what I call the new DBification of ML AI. And then I will pick two concrete examples from my recent research, to exemplify this theme of DBification. Then I'll talk about how we can accelerate DBification of ML AI. Okay, so what do we care about in ML? Primarily, if you look at the ML algorithms, like the NeurIPS, ICML, ICLR types, they overwhelmingly worry about accuracy-related metrics, AUROC, precision recall, BLEU score, whatever. Sometimes they also worry about runtime efficiency metrics, typically often in the form of computational complexity, but also inference times or training run times. But in the ML systems world, there are additional practical concerns that we need to worry about as well in an entire Pareto, multidimensional Pareto surface. What if your data set is too large for your machine memory? That is the concern of scalability. And not just scaling to large data, you need to be efficient, resource efficient at the large scale as well. How are these features and model architectures, how are they configured to make things actually work? That's the concern of usability. How do these software fit within production systems and workflows that are existent in these organizations? That's the concern of manageability. And how do you simplify the implementation of these sorts of systems? Because developers have to write these. That's the concern of developability. Now, if you look at these concerns, we have been studying these sorts of concerns for decades in the database systems world, albeit for relational and SQL computations. Now it's time to study these sorts of concerns for ML computations as well. Now, there is also an interesting bit here. Often machine learning, you can trade off a little bit of accuracy to gain enormously on one or more of the rest, like scalability, manageability, and so on. And so that leads to novel technical issues, novel problems that we can study beyond what we just know in the database world. It's not just me who's talking about this. Google had this famous paper, Hidden Technical Debt in Machine Learning Systems in NIPS 15, now NeurIPS. And here they identified, like, if you look at the ML code that these ML practitioners write, it's like this tiny little piece in the middle, and then you have all this sprawling infrastructure around it, collecting data, verifying data, feature extraction, resource management, monitoring, and so on. And this is what they call the platformization of ML. Now, if you look at the history of this field, platformizing ML has been happening since the 80s. That's when the SAS Institute started. And even today, SAS is one of the most widely used enterprise analytics tools, especially for statistical relational analytics. Just statistical and relational data analytics. S is an open source language that later became R, and R is hugely popular in the statistics community, biostats, and many other domain sciences. But in the late 90s is when the database systems community got involved, and they built these in our DBMS ML systems. So these are also called data mining tools back then, though nowadays the term data mining means something else. So IBM, Oracle, Microsoft SQL Server, they all came up with these tools where ML algorithms were integrated into our DBMS process execution spaces using user-defined functions and user-defined aggregate functions. So now you could invoke training and inference as part of your SQL console. And they understood how to scale some of these algorithms using these abstractions of DBMSs. But later, in the late 2000s, data flow systems started taking off. MapReduce, Hadoop, Revolution, and then subsequently Spark. And people started integrating ML on top of these data flow systems as well. Apache Mahout and Spark ML or Spark ML lib. They also write ML algorithms on top of abstractions like map and reduce or other APIs like the RDD APIs. They are also used in many settings. But in the kind of early 2010s, people realized that we need to do something more rather than just go around building one algorithm at a time. That's where people came up with these ML system abstractions, unified templates to build mini algorithms in a simple way. Apache Madlib is one of those, which integrated with PostgreSQL and Greenplum. I have been involved with that. GraphLab, another one for graph parallel machine learning, and Parameter Server that came out of Google. And these sorts of ML system abstractions started gaining popularity. And then in the mid-2010s, we've seen the rise of tree learning systems and deep learning systems. Tree learning systems, also called gradient boosted decision tree, GBDT systems, are wildly popular on tabular data in the real world, especially in enterprises. XGBoost, for example, is very common for structured data prediction tasks. But anything that is unstructured data, text, time series, even images, video, and increasingly also for data integration and data cleaning tasks. Deep learning is now the way to go. And TensorFlow and PyTorch were custom-built systems to make deep learning more practical. And in the last few years, the cloud giants have come up with established platforms for running ML and AI as services. So SaaS software service. SageMaker is a good example. Google Vertex AI is another, Azure ML. And then there's also this notion of platforms and feature stores that are open source that people can use. TensorFlow team came out with TensorFlow Extended from Google. Databricks released MLflow for managing the whole lifecycle of projects. And then there's feature stores, which kind of abstract out certain functionalities, and Tekton is a good example. And so this whole community has become much larger to study how to platformize and systematize ML. The way I see it, this rise of the ML systems and platforms world resembles the rise of relational DBMSs as a category of software systems circa early 1980s. That is why I call this the new DBification of ML AI. What we did for relational SQL computations, we need to do for ML computations. And we need to do this across the whole life cycle. Let me highlight some examples of research challenges here that the database community needs to step up on. In the source phase, metadata management for ML is an important concern. People fuse different signals and different data sources. You need to have our experimentation data. Reproducibility is important. Data preparation and cleaning is still a huge nightmare. Often it's very manual and very tedious. Can we come up with better ways of doing it? Multimodal data is becoming very common, especially in like recommender systems and web applications, image, text, and tabular integration, coming up with query interfaces and execution engines for that. Data search systems, especially on data lakes, where you have, I don't know, millions of files and their metadata is scattered. How do you make it easier to locate the data you need? Data labeling systems, how do you get supervision data? All of that is important. And on the build and deploy phases, a lot of system building stuff, scalable data systems for machine learning workload is still an active research area. And then query optimization that we did for relational context, we need query optimization for ML context as well, making sure that these systems are utilizing the system resources efficiently. And increasingly, a lot of ML analytics is being done in the cloud. So making sure cloud native systems work well, streaming, online inference, serverless, all of that is also important research challenges. And overarching process, because there's a complex pipeline involved, provenance management, debugging when things fail, error detection and correction, these sorts of issues also involve a lot of data management issues. And across this whole thing, when people build new systems, immediately you have to wonder, how do you compare them on an even footing? Benchmarking is very critical here. Benchmarking of frameworks, not just for ML training and inference and lifecycle management, but also coming up with benchmark data sets, label data sets for things like, say, automation of some of these tasks, like data preparation. And we talked about systems concerns, usability concerns. There are several other concerns also that people need to worry about in this whole context. Fairness of predictions, especially avoiding disparate impact across protected demographic categories, transparency and explainability, privacy, security, all of those issues also matter. And so this has become a huge sub-area at the intersection of data management and ML. And I think this is an exciting area for us to study. Now, in this context, what have I been doing in my research? Overwhelmingly, my research has focused on three things here. On the source side, we studied a lot of metadata management, multimodal querying, and data preparation and cleaning, especially creating data sets for that. We have studied very intensively on scalable data systems, execution engines for both statistical ML and deep learning, and also query optimization methods. We've introduced this notion of multi-query optimization, materialized views, and so on for machine learning systems. And we've also worked a lot on benchmarking of ML systems, comparing their efficiency, scalability, and creating benchmark label data sets. I will talk about two of these examples today, one from the world of scalable deep learning systems, and two from the world of automated data preparation for ML and creating benchmark data sets for that. Any questions so far? No? Okay, let me proceed.
Any questions in the room or online?
I don't see any on the chat, so I can proceed. Yeah. Great.
Okay, I think no questions for the moment.
Sounds good. Okay, let's dive into the first one, scalable deep learning systems. How do you imagine deep learning at scale works today? You would think, okay, I write my neural computational graph in PyTorch or TensorFlow or Keras, write out the neural computational graph, train it with stochastic gradient descent, give it to my cluster. Maybe it's using Kubernetes to manage it, GPU, CPUs, memory tests, and it works. The unfortunate thing is that's a very rosy picture because deep learning model building is never one and done. You need to run this whole process called model selection, and that needs to be done efficiently at scale. Model selection involves tweaking and tuning these models in various ways. So in Project Cerebro, we took a holistic view of this whole model selection process. I'll talk about what these tweaking and tuning include: hyperparameter tuning, architecture tuning, feature selection, data subset selection, and so on. These higher level APIs already exist, like in Keras, AutoML heuristics, and so on. And what we do is we intercept it at that level. The user can still use the same PyTorch and TensorFlow for the computational graphs. And then we infuse what we call multi-query optimization for deep learning. You have multiple models being trained on the same data. Let's share data moments, share computation, share many things that allow us to improve resource efficiency and reduce times. And then Cerebro will place the computations on the cluster for the user. This decoupling of what the workload is about from how the workload is executed also allows us to do portability. With the same code stack, we can now run the workload, say, in a cloud-native fashion or on a Spark cluster. And we have integrated Cerebro with Spark cluster as well. Now, this philosophy of separating the what from the how is obviously integral to how relational DBMSs work, right? So that's declarativity, data independence. We call it by many things, logical physical separation. We were bringing this philosophy to the world of model selection and deep learning. So what is a good concrete example of multi-query optimization? And I'm going to dive into one of those, which we published in VLDB 2020. And this is the first full paper from the Cerebro project, so that's why I'm picking this one. Hyperparameter tuning is pervasive. Every time you train a deep net, you have to worry about your learning rate, regularizer, batch size, maybe dropout, and you have to set these hyperparameters somehow. There is no one size that fits all. You can't use a universal set of hyperparameters across all data sets and tasks. You will underperform, you will waste your label data. There's numerous algorithms for hyperparameter tuning. We're not worried about the specific heuristics for hyperparameter tuning, hyperband, ASHA, so many things. There's also architecture exploration. You might clip some layers, add some layers, fine-tune some layers. All of this leads to numerous training configurations to run on a large data set in one go. That's why it's a multi-query task. So how would we run this? If I give you, say, 20 models with different hyperparameter combinations or different architectures and a training data set, how are you going to run this at scale? Let's compare with how people used to do it versus what we do. Our strategy is called model hopper parallelism. But let's compare what people used to do. In the ML world, task parallelism was very common. What you would do when you're given multiple set of models to run on the same data, and you're given a machine cluster, is you copy the data set literally to every worker. So here the picture shows D placed on every worker. You assign a different model to each worker, and then you run them in parallel. So one worker per configuration, and you execute this in parallel. That's great. However, although it gives you high throughput for execution of model selection, you're training many models, you can compare many models in parallel. It's also great for accuracy because you're not messing around with the stochastic gradient descent process for SGD. The sequential execution of SGD on the worker gives you gold standard accuracy, best convergence results. However, as we know, it's not very scalable from a data standpoint. If I have a terabyte of data and I have to run this on a 10 machine cluster, now I've bloated this to 10 terabytes of memory and storage usage on my cluster. If you're sharing a cluster, that's kind of unethical if you're hogging resources like that, especially on campuses. And if you're in the cloud, you're going to be spending extra money to get extra machines with more memory and storage and stuff. So you waste space. Alternatively, you store the data in a remote machine and then you read it in a streaming way over the network. But SGD is iterative. Sometimes you train models for even dozens of epochs, even 50 epochs. And if you're comparing dozens of models and dozens of epochs, now you're streaming the data hundreds, even thousands of times. You're wasting the network enormously, causing huge amount of unnecessary traffic. So that was the world of task parallelism. Now, we as database systems folks know that the best way to scale to large data is data parallelism. You shard the data into these D1, D2, D3, or partitions, whatever you want to call them, put them on these workers. Now you assign a single model to the whole cluster, and then you train them in a data parallel fashion. So here, for example, parameter servers have a server and then they communicate with the worker. There's other tools like Horobot where there is no server, but the workers talk to each other. Regardless, what they do is they update the model after seeing every mini batch of data, but that update requires a lot of communication. And so what you end up with this world of Horobot and parameter server and all of that is you get data scalability via sharding. However, because you are communicating at every mini batch, your communication cost is almost 3-4 orders of magnitude higher than the task parallel version. Every mini batch is probably dozens, maybe hundreds of training examples. But a single shard in your large scale data could be millions, tens of millions of examples. So now you're communicating thousands of times, even just one iteration of one pass over the data. Alternatively, you can say, why don't I just communicate once per shard? That is called model averaging. We know that does not work well for deep learning. It works for linear models and convex models, but it does not work for deep learning. It won't converge. So you won't get good accuracy. And so because you have these high communication costs when you communicate at mini batch level, tools like Horobot give you poor throughput for your model selection process. They're great if you have only one model to train, but they are not great if you have several models to train in a model selection scenario. So this is what we looked at, this world, dichotomous world of task parallelism that the ML folks liked, data parallelism that the database and systems folks liked, and we brought the two together and said, why don't we get the best of both worlds? That is what model hopper parallelism does. It's a new hybrid of data and task parallelism that gives you the advantages of both without the disadvantages of either. So how does MOP work and what is it based on? MOP is fundamentally rooted in a simple insight from optimization theory. Now, when we look into the literature on stochastic gradient descent, it says that you need to randomly reorder the data. It's called shuffling. You can't access the data in an ad hoc order. You'd have to shuffle it, and then you access the training examples in a random order. But HGD does not care what randomness of that ordering is. Any random ordering is fine for HGD to converge. So let's do the following. Shuffle the data set, partition it across workers, and place the shards on the workers, just like you do with data parallel tools. Right? So it's very similar to data parallel. You have 4 shards on 4 workers. But now, similar to task parallelism, you assign different models to these different workers. And you start their training in parallel, like task parallel way. We call this the first sub-epoch. Each model looks at its local data, finishes training on that local data, one sub-epoch. At that point, checkpoint the model, hop across the workers. And now resume training for that model on the next worker for the next sub-epoch. Each model keeps hopping across all these workers until it has seen all the shards of D, it has seen the whole data set. You have finished one epoch for that model. That's why it's called model hopper parallelism. Now, if you think about this, what is going on here is we are running sequential HGD. Every model is visiting the data in a sequential order, albeit it's a different level of randomness compared to other models. But HGD doesn't care. All model randomness is fine. And second, we showed in the paper that this approach hits the lower bound on communication cost for data parallel model selection compared to, say, task parallel or data parallel approaches. This hybrid gives you an optimal, resource optimal approach for doing data parallel model selection. Now, one thing to note is this sounds deceptively simple. Why haven't people done this? It's like people haven't thought about putting these worlds together in this way. And although the basic idea is simple, in an actual system implementation, we have several challenges that we've tackled. We want this to be a generic resource-aware scheduler. We should be able to support, for example, machines where you can place different neural architectures with different computational times. There is no synchronization point across these sub-epochs. Models get placed on workers when workers become available. We call this in the paper bulk asynchronous parallelism. Now we know bulk synchronous parallelism in the database systems world. This is the first known example of bulk asynchronous parallelism. And this can work for evolution of model configurations. Like these AutoML heuristics, they change the model configurations after every epoch. And our system, Cerebro, can actually handle that as well. It schedules this at every epoch level. It can support data replication. Sometimes you copy the data sets across, say, 2 or 3 machines to give fault tolerance. It supports fault tolerance. If a machine fails, Cerebro will be able to restart it elsewhere. It gives you elasticity. If you throw more machines at a future epoch, you can copy the shots or you can reassign the work. All of this we showed can be done in a non-destructive way. We integrated this with PyTorch and TensorFlow without needing to change anything in their internal code. All we needed was this checkpoint and resume API, which these deep learning tools already provide anyway. And so the rest of stochastic gradient descent algorithmics, the computational graph, the compiler, none of that needs to be changed. And this makes it more practical for adoption purposes. Any questions about this? Okay, let's see how this works. I said this model hopper parallelism is near resource optimal. Let's see if it actually stands the test of an experiment. We've taken a benchmark ImageNet dataset. It's a common computer vision benchmark in the deep learning world. And it's we just took 16 CNN configurations, 2 state-of-the-art models back then when we published it, with 8 configurations each. Implemented in TensorFlow, we ran it on an 8 GPU node cluster here on campus. I'm going to show you 2 things. So on the plot here, on the x-axis, I'm showing you the epoch number, and the y-axis is the benchmark accuracy metric. It's the validation error, the top 5 validation error. Lower is better. And so this is called the learning curve. As the epochs progress, you want the curve to drop. And I'm comparing 5 things here. First one is TensorFlow model averaging. This is the one where you communicate after a shard. So you communicate once per pass over the data. And that does not converge very good because, like I said, model averaging doesn't work for deep learning that well. AutoML is the state-of-the-art data parallel tool. It uses high-performance computing techniques called all-reduce, and it gives you good convergence behavior. TensorFlow parameter server, asynchronous, ships natively with TensorFlow, and that also works well. And there is a gap you see between Horvath and parameter server. That gap is an artifact of Horvath's mini batch sizing. You can actually bridge that gap by readjusting the mini batch. But then let's compare Celery. Celery is a task parallel tool like Dask or Ray, and you basically copy the data set and you run it in a task parallel manner. It gives you the best accuracy, has parameter server as well. And then you have Cerebro. It basically lines up with Celery. The learning curve is virtually indistinguishable, and it reaches the best accuracy too. But now let's look at resource metrics. On runtime, parameter server is almost 10 times slower than Celery and Cerebro. Horvath is about 3 times slower. Model averaging is roughly the same time, but it does not converge. And if you look at space, memory footprint, Celery, because you had to copy this 200 gigabyte data set, loads to 1600 gigabytes. Whereas Cerebro keeps the data set as it is in the sharded manner on this 8-node cluster. Overall, Cerebro offers the best combination of both accuracy and learning behavior and resource efficiency, both space and time. And we have more detailed experiments in the paper, including other workloads for model selection, AutoML heuristics like Asha, how does that work on Cerebro? And then we sliced and diced the components of Cerebro to see where the efficiency gains are coming from and so on. And I'm happy to take questions offline or over email as well once you take a look at it.
All right. Any questions at this point? I would be a quick one, but
Hello, my name is Sam. I have a question.
Yes.
I guess the assumption here is that the data size, like the data is much larger than the model in general. So that's why we're like communicating the current models instead of like switching or communicating the data. And I guess like recently there's a lot of interest in like pre-trained models, and they have billions of neural, and they're really big in size. So, but I guess still the data set will be bigger in that case. And I was just wondering like how this could help like those really large models.
That's a great question. So the regime you're talking about, sorry, can you hear me? Thank you for the question. So,
oh, yes, I can. Yes.
Yeah, so the regime we are talking about here is large scale data. The regime you're talking about is large scale model. We actually have another project called Hydra in part of the Cerebro umbrella, where we exactly come and visit that question. Let's say the model is too big and it doesn't fit on GPU memory. Now we need to run it on multiple GPUs. How do you do that? There's an analog called model parallel systems. There we showed that model parallel systems also underutilize resources and have high communication costs. We came up with another hybrid strategy that we actually showed can give you resource efficient performance. That's a separate paper. I'm happy to chat about that. But in the grand vision of Cerebro, data scale and model scale will be supported together. The model scale problem is also real and it's also common. For example, when you download models from Hugging Face or whatever for text fine-tuning, your text data, label data could be very small, could be just a few gigabytes. There, you just copy the data set across machines, but your model could be very large. It could be dozens of gigabytes. So in that case, you'd have to resort to sharding the model instead of sharding the data. Okay, so we've studied that. I'm happy to chat more about that.
Got it. Thank you.
Awesome. Maybe very quick question. I think that those relative performance numbers, I mean, they might also depend on the hardware properties of the cluster, particularly the quality of the network. Is that something that you did you vary the hardware setup, or which hardware are you using there?
So this was V100s back then. That was what was available. The network was a commodity network on our cluster on campus. And one other thing we showed was if you do remote reads, for example, on AWS, there you could actually run task parallelism by remote reading the data. And we showed the gap in the network traffic that takes place. We're talking 3 orders of magnitude gap in the network traffic. Now, increasingly, people are trying to build, say, optical networks, for example, in the cloud. Now, then the tools like Horovod, the communication cost, even though it still exists conceptually, the latency of the communication can reduce. People also overlap communication and computation and stuff. It'll still fundamentally still be slower because here we are resource optimal and we are the lower bound. However, the cost of those hardware is another thing you would have to pay in addition to the cost of the processing and the memory. And so there will always be a spectrum in the Pareto surface of the axes that I mentioned, right? Cost and training time and accuracy and stuff. And it depends on which application you are in. If you're like the Facebooks or Googles, you can afford very expensive hardware. If you're domain scientists, if you're enterprises, probably not. So I think that's sort of where the world will be.
Okay, that makes sense.
Okay.
Actually, I have one more question.
Yeah.
So, some configurations might be faster to train than others, and it's in the paper. But could you briefly explain how you deal with the different?
Sure. Yep. So in general, so here this illustration kind of shows you 4 graphs, right? 4 models, 4 computational graphs. In general, your model selection workload could be even larger. And so what we have is basically a scheduler that's a generalization of what we call open shop scheduling. It's a simple scheduler that will assign work to workers when workers are free. And so there is no synchronization that is necessary across workers. And even if different models have different computational load, the scheduler will automatically take care of this kind of load balancing aspect of assigning work to workers. And we showed in the paper the simulation comparisons with the Gurobi optimal schedule versus our scheduler, and our scheduler is competitive with the Gurobi optimal in terms of make span, but in terms of latency of running the scheduling, it takes milliseconds.
I see.
Okay. Yep. Okay, so that was model hopper parallelism. The whole vision of Cerebro we published at CIDR last year. I gave this talk at the CIDR conference. And here we showed how we are bringing this philosophy of layered stack for deep learning workloads with 3 layers. The highest level is your model building APIs. We talked about hyperparameter tuning, there's architecture tuning. Somebody talked about transfer learning and fine tuning as well. We've published about that as well. Feature transfer, ablation of architectures, learning separate models for separate groups in the data, sequence analysis, graph analysis. So we are studying all of these high-level model building APIs. You can use a command line interface. You can use Jupyter notebooks. We've also built a graphical user interface for intermittent specification of model selection. At the lowest level, we have the execution and storage layer. And they are agnostic to what people want to use. People would use different things. Like many people have on-premise clusters run in Kubernetes, for example. Some people use Spark clusters. We've also integrated this with Greenplum in collaboration with Pivotal and VMware. Or some people might just run it on a cloud-native fashion. In the middle is our secret sauce, the optimization and scheduling layer, where we run these sorts of hybrid parallel techniques, model hopper parallelism, the other parallelism techniques for large-scale models that I mentioned, transfer learning, materialization management, memory management. All of this wraps around an autodiff and SGD execution engine, which is TensorFlow or PyTorch. And so we don't need to change autodiff or compilers. So if TensorFlow and PyTorch evolve in the future, we can just drop them in here and nothing will change in Cerebro. On the side, we manage all the metadata that is produced because you're training so many models. You want to make sure you can artifacts and all of that you can log and visualize. We use MLflow for logging and TensorBoard for visualizing and stuff. We've integrated Cerebro with those. And all of this can happen in a fault-tolerant and elastic manner. So to summarize this whole vision of Cerebro is a model selection first, layered data platform for scalable deep learning. It combines higher level specifications for deep learning model selection and model building, fine-tuning with multi-query optimization techniques, stuff that we have studied for decades in the relational world. This is the first to bring it to the deep learning world. And we showed that this can give you better resource efficiency, sometimes even resource optimal performance, and improve deep learning users' productivity, because now they don't have to worry about copying data to multiple machines or running Horowat and running it slowly. The faster you're able to explore different configurations, the more productive you are in coming up with better models. We have used this for public health scientists here on campus. And so this is part of some of the early adoption we've seen. They have terabyte-sized label time series data from accelerometers. And they had a prior stack based on physics-based features and statistical models and decision tree ensembles. And we raised the accuracy from 77 to 92% for a binarized version of this task. All we did was commodity CNN and LSTM architectures. Cerebro, because of its high throughput parallel exploration for large-scale data, allowed us to get to a better accuracy. And we're also doing the collaboration that's ongoing with computational physicists. And here it's in the large-scale model regime. So one of the questions was, what if the model won't fit in GPU memory? We've actually studied systems for that as well. And model hopper parallelism has been adopted by Pivotal, like I said, for MadLib as part of deep learning on Greenplum resident data. VMware has shipped it for their enterprise customers. We've also open sourced a release with integration with Spark, so you can run MOP on Spark. And we are integrating more workloads, including creating this unified scheduler for all these sorts of optimizations. And we're going to integrate it with the San Diego Supercomputer Center here at UC San Diego. They are building a 100 accelerator cluster called Voyager in partnership with Intel. And there's like 20 domain scientists who are going to be using it. And so we're hoping Cerebro will be able to benefit data scale and model scale problems for all of them in the near future. And I'd like to thank all these funding agencies for their generous support of this project. You can see it's a diverse set of organizations and that we're excited about this area of work. Okay, so any questions, or shall we move on to the second part? And the second part is going to be much briefer. I guess we can continue and answer your questions.
Questions by anyone, or? Okay.
Okay.
Maybe I think it's fine.
Okay, so the second one is just changing gears a little bit. We're talking in the data sourcing stage. This example is data preparation. Now, there's this trend of AutoML platforms, automated ML platforms, that are claiming they can automate your hyperparameter tuning, algorithm search, and all of that. And that's great. A lot of data scientists do use AutoML tools now. And sometimes organizations that don't have data scientists, they use AutoML tools to kind of feasibility test whether ML is useful for their applications. And then they might hire data scientists afterwards. So AutoML tools have been gaining traction. So several of them have released products. Some cloud companies have released products. But what I saw in this whole spiel is they were claiming they have automated data transformations too. So like this is Transmogrify from Salesforce Einstein, which is apparently used on hundreds of thousands of data sets by tens of thousands of enterprise companies. And so they say transmogrification means you give your raw data file from your database, we will transform everything and get it ready for ML. Great. Autopilot from SageMaker, AWS, also claims the same thing, automatically transform data. TensorFlow Extended also has transformation routines, although it doesn't claim automation, but it's interested in it. And we looked at this landscape and we said, so they're claiming they've solved data preparation with automation. But how good is it? It's fine and nice to say I've automated it, but if it's crappy, it's no use, right? Your accuracy for ML is not going to be good. And we were shocked that no one really knows objectively how good such automated data preparation is. That's where we came in and we said in Project SortingHat, we need to define benchmarks in this space. Just like the ImageNet benchmarks did, the Spider benchmarks for NL to SQL, and so on. And also the TPC benchmark for performance and runtime performance in RDBMS. We were inspired by these benchmarks across these communities. And we defined benchmarks for ML data preparation. Now, we decided there needs to be 3 parts to this benchmark. One is we need to formalize the task definition. Data prep is too wild and kind of too broad. Specify what the inputs are, what the outputs are, what the semantics are. So we need a suite of task definitions, not just one, for benchmarks for data prep. 2, you need to create labeled data sets, input-output pairs for that particular task. This will help you assess accuracy of different ways of automating that task. And the third one is it's not enough to just automate the task. The task is in service of building an ML model on the data for, say, churn prediction, sales forecasting, whatever it is. You need to evaluate the accuracy of that automatically prepared data being used for that ML training. So you need the downstream models predictions to be evaluated. If I do a data prep in method 1 versus method 2, how does it affect the model's accuracy that you build on it? So we need downstream prediction benchmark as well. And from a scientific standpoint, we realized that this was a gaping hole at the intersection of ML and databases because the ML community has studied to death how to optimize and kind of automate hyperparameter tuning, feature selection from a statistical and learning theoretic standpoint. The database community has studied data preparation and data cleaning for SQL analytics, for business intelligence and stuff. But now when you're looking at this for ML, how does data prep affect ML accuracy? Literally no one knows. And so we realized there's a lot of open theoretical questions here as well in terms of the impact of data prep steps on the bias variance trade-off of machine learning classifiers, for example. How do we quantify this? How do we build in, based on this understanding, fail-safes that can, maybe in an automated system, allow you to explore alternate paths and then avoid downstream prediction quality degrading. So this is why we got started on this. We call it the ML Data Prep Zoo. In the Dean workshop paper, we laid out this vision of 6 common tasks that we saw happening in many settings, and that we saw many of these open source data prep automation tools trying to automate with rule-based heuristics. And one of those tasks is, the first one is schema inference. So in this example, you see, you upload a CSV file into these tools. You just export from a database. Each column, like zip code, for example, is stored as an integer. Right? In a database, you have integers and strings and so on. But ML doesn't operate on that. It operates on a vocabulary for features, like categorical, like numerical. And one of the tricky things here is if you have zip code as an integer given directly to an ML model, it'll treat that as a number. And now you'll be interpolating in a hyperplane for logistic regression and stuff, and it'll be just garbage results. Somebody has to intervene and then say zip code is categorical, cast it to a discrete set. That is the part of schema inference. And so like we defined a vocabulary for this ML schema inference based on our survey of the space of different tools. It's a 9-class vocabulary with numbers embedded in strings, for example, like income. Even though it's a string, everything else is a number. There's just one thing that's a string. These sorts of timestamps, like time since, for example, these sorts of base features have to be identified before you could do any ML automation on it. And so we studied some of these tasks. We've studied the category deduplication as well. Some of these other tasks are still open. And we hope that by open sourcing these data sets and these benchmarks, community contributions can come in and more people can study these sorts of problems, because I think this space is far larger than any single researcher or any single group can study. So for the schema inference task, we built a benchmark data set. We compared classical ML models built on that data set, labeled data set with cross-validation, even a CNN model. And we showed that that actually beats the schema inference accuracy compared to industrial AutoML tools like AutoTFX at Google, AutoGluon from Amazon, Transmogrify from Salesforce, significantly. And these details are in the Sigmod paper. What that means is their rule-based approach to type inference was brittle, whereas our learned approach to type inference was much better in the accuracy and also the accuracy of the downstream models they built. And so Google was excited about this. Amazon was excited about this. They gave us gifts generously. And we've collaborated with the TFX team, the TensorFlow Extended team at Google over a couple of years, integrated this with TensorFlow data validation, open sourced that too. They have benchmarked this on their internal AutoML benchmarks. They haven't told us if they're actually using it, but they said they have 100 downstream data set benchmarks that they're testing it on. Amazon, we collaborated with the AutoGluon folks. It's integrated with that. we also integrated this with OpenML, which is an open source community repository for data science artifacts run by Joaquin and his team. And AWS, AI, and database teams also explored some of this. The model that we built for classifying feature types has also been open source and has been contributed to some of these tools, including a search tool for models and data sets called AI Maker that one of my colleagues here is working on. So this whole landscape of data prep, I think coming up with benchmark data sets can potentially lead to interesting ways to have impact on this space and improve the automation of end-to-end data science pipelines. Any questions? That's all I'm going to say about this. There's a whole talk on this. I'm happy to send you a link to if you're interested. Okay, so let's proceed. So this is basically two examples, one from the source stage, one from the build stage of what we saw was the DBification of ML AI. Why bringing data management and database systems know-how into the ML and AI world can benefit that world, improve life for practitioners. I hope more people start studying these sorts of problems, because if we leave these problems open, it's going to result in a huge waste of time, manual effort by these data practitioners, ML practitioners, effort, money by many of these organizations, and also academics, and energy, especially in the deep learning context. And do we really want this to happen? If we let this happen, that's a shirking of our intellectual responsibility as scientists to both science and to wider society. And so I hope it's now time for the database community to partner with the ML community, AI community, and other areas to join forces and accelerate this DBification of ML and AI. Okay, so now last brief comments about how I think we can accelerate this DBification of ML and AI. These are not exhaustive. This is just my thoughts based on my experience in this field. So make what you want of it. Obviously, from the database community, if you are moving into this space, you have to learn the fundamentals of ML AI algorithms and also ML theory if needed. It's kind of like learning the basics of logic, relational algebra, and SQL if you want to work on relational DBMSs. If you don't know those things, it's going to be tough for you to work on relational DBMSs. Review ML algorithms classes in your institution or online. There are great courses also. And these are some of the books that I recommend: Hastie, Mitchell, Kurbel for machine learning, statistical machine learning, and deep learning. And you don't need to learn everything up front. If you're working on deep learning systems, learn about deep learning first. You don't need to learn about statistical ML as much. If you're working on ML theory, if you're doing accuracy trade-offs, learn a little bit about ML theory, bias variance trade-off. You don't need to learn about deep learning as much. So need to know as you grow, you can learn more. And there are courses in this space now. One of my courses is the first courses in this space in the world, Data Systems for Machine Learning. I created this when I joined UCSD in 2016. I created this in 2017, taught this 6 times, including this quarter. And the 2020 edition, I've created YouTube lectures, and they're all available on my YouTube channel, so feel free to check them out. The slides are also public, so feel free to check them out there as well. And I also worked with Matthias Bohm, now at TU Berlin, and Jun Yang at Duke to write this book, invited book by Morgan and Claypool, Data Management and Machine Learning Systems, the first research-oriented book in the ML system space. And PDF of this is free in academic networks, so do check that out. There are several excellent tutorials in Sigmod and DLDB by this DB for ML community. We gave one of these tutorials, which led to the invited book. Then there are several others that have also given some excellent tutorials, including on data integration, data quality, and stuff. Do check those out. And go to these workshops. Data Management for End-to-End ML Dean is a really nice workshop. It's a eclectic mix of database systems, ML, HCI folks. Very exciting stuff goes on there. Hilda, Human in the Loop Data Analytics, is also an exciting space for some of this work. And there's this new conference that started a few years ago. I was part of this founding white paper, MLSys, where a lot of systems for ML work happens. It's a little bit more systemsy than Sigmod, like there's compilers people, architecture people, and so on. But it's also an exciting, eclectic environment. I've also run some topical panel discussions on this space. Both of them have blog posts on the Sigmod blog, so go check this out. I like to be provocative. So, you have to have the audience riled up a little bit so that it's energetic. So I called, is it snake oil? Are we losing relevance? All of that stuff. And most important, while we're doing the research and advancing the foundational science and technology, also collaborate with actual users. Speak with ML/AI users in domain sciences, in enterprises, web companies, wherever you can collaborate with. Work on real problems to translate your work to practice. Build software, real software that they can use, build real data sets, benchmark data sets, artifacts that you can open source. And you could collaborate with data scientists, data analysts, so many data plus ML practitioners now, several job titles too. They all do different parts of the life cycle. And personally, I also like attending industry conferences other than the research conferences. Spark Data AI Summit is one that I really liked. There's also FOSDEM. There used to be Strata, but that's no longer there. So check out one every couple of years or 3 years or so if you're interested in research. A lot of practitioners come there to give talk about what they're doing, how they are using these tools, what their bottlenecks are. And I learned a lot about the whole life cycle from going to these sorts of things. And publication, apart from the regular research categories that you publish at VLDB, I helped launch the scalable data science category under the research track. Ran it for 2 years. A report on this is also available from the first year in Sigmod Record. Go check it out. And this is kind of integrated research and research plus practice in the space of scalable data science. We hope this is beneficial for the VLDB community. Sigmod has its own analog of this, and now ICDE also has an analog of this. MLSys, I already mentioned. And KDD has also had this applied data science track from before. Some systems papers have been published there. So there's several avenues in these research conferences also for you to publish work in this intersection, apart from the regular research ones. So to conclude, I hope the database community steps up to this grand challenge of DBification of ML AI to help democratize ML AI. Partner with folks in the ML community, AI community, systems, HCI, any other community that you want to bring ideas from and kind of translate ideas from, and work with actual users in domain sciences, in industry, and collaborate with them to translate your work to impact on practice. I'd like to thank all these terrific students who've been doing all this work, and I'm the one talking about their work. And so all these students have been involved with many of these projects. Supun has been leading some of this stuff. He graduated earlier this year, he went to Databricks. And Vraj has been doing some of the SortingHat stuff, and he graduated earlier this year and went to IBM Almaden. And with that, I'll conclude. All the projects, code, data, artifacts, papers, talk videos, blog posts, everything is available from our project web pages. Go check out uscsd.github.io. Feel free to follow me on Twitter if you want updates sooner on our research. And I'll stop here, and I'd like to thank all these other sponsors of my group's research, and I'll take questions now.